Hello and welcome everyone. My name is Jason. I am from the Athena Research Center team in Athens, and I work on the medical informatics platform where I help develop the analytical tools, mostly statistical algorithms and machine learning algorithms for the MIP within the HBP project. In this talk, I will present the process we go through in order to build and validate new federated algorithms. I will start by defining the problem we have and then and also discuss the tools we have at our disposal. I will show you step by step the basic reasoning on a small toy example. And from there, I'm going to formulate a more general method and apply it to a more realistic example. Then in the end, I will go through the validation process that we follow for each new algorithm. So, what is a federated computation in our case? So in the most simplified form, a federated computation in the MIP takes place in a network of computational nodes. There are multiple hospital nodes where the clinical data are kept, and there is one central node where some information can be gathered from the hospital nodes. We are given a particular computation to perform over the data that is distributed across multiple hospital nodes, and where this data is confined and it's not allowed to leave. And our goal is to come up with the result of the computation. And this result has to be identical as if the computation had taken place on a single machine where all the data is present. With that in mind, let's now see how these algorithms are implemented and what tools we have at our disposal. The hospital nodes execute what we call local computations. These computations have access to the clinical data present in the particular hospital node. The central node executes global computations and itself has no access to any clinical data. We can think of these computations as boxes where we can write code, arbitrary code, and we can have many different kinds of local and global computations, as many as we like. What the system does, in a nutshell, is to execute these computations in a particular order and to allow the nodes to transfer some results to other nodes. So the hospital nodes only transfer data to the central node, so there is no communication between the hospital nodes, and the central node can transfer data back to the local nodes. An algorithm consists of a particular flow between these local and global computations. At the moment, we have the possibility to allow some predefined number of steps or a repeated execution of steps until some convergence criterion is met. Currently, we're working on expanding these possibilities to any arbitrary workflow. In order, therefore, to implement an algorithm in our federated environment, we need to answer the following questions. First, how to decompose an algorithm into local and global steps. And second, what kind of information should the nodes exchange? I will answer these questions starting from a toy example and then attempt to give a more general solution. Let's say that we are asked to compute the average of some quantity in a federation with just two hospital nodes. So we have some quantity in hospital A, we have some other quantity in hospital B, and quantity, I mean some measures, some repeated measures of a particular quantity of interest. And then we want to compute the average, the global average. So the average is a very simple computation, but it contains all the ingredients that we need in order to illustrate the challenges of a federated computation. Now, how are we going to design these federated algorithms? This design will be guided by two principles, which tend to be in competition one with the other. So on the one hand, we want to protect the privacy of the clinical data. We don't want to expose individual data points outside of the hospital nodes. And one condition we impose for this particular for this privacy restriction is that the only information allowed to leave the hospital nodes are aggregate information. So it's aggregates of a large number of data points. On the other hand, the second principle is that we want to obtain exact results, and by that I mean the results that are identical to the non-federated case. So what does this mean? It means that there are some operations that can be parallelized, they are parallelizable, and then these operations can be distributed across all the hospital nodes and then merged together. And other operations cannot be parallelized and have to be centralized if one wishes to obtain the correct result. At this point, I must say that it is well understood that exposing aggregates is not a real privacy technique. For example, some malicious party would be able to infer individual data points using multiple queries and then looking at the differences between those queries. However, once the algorithms are designed with this condition, so the aggregate condition, then some more advanced techniques covered in other talks like secure multi-party computation and differential privacy can be added on top of the existing implementation, and which provide a true privacy guarantee. So I will proceed with this simplified privacy mechanism, but bear in mind that it can be enhanced with much stronger and much more robust techniques. So let's make a first attempt to solve this average problem. So we can try to completely centralize computation. We can pull all the data to the central node and then just compute the average, and that's it. Of course, this is correct, but obviously it violates the privacy condition that we have mentioned before, because we are just exposing all the individual data points to the central node. So this is not good. The second attempt, for the second attempt, we can go completely the opposite way and try to localize as much as possible the computation. So here we can compute all the averages locally in each hospital node, and then we can try to magically combine all these results on the central node. But of course, it's easy again to see that there is no way of combining these local averages to get a correct solution, because this operation is not parallelizable. The correct solution lies in a sweet spot between the completely centralized and the completely localized case. And actually, we just compute the sum and the length of the data locally. We share all these quantities, which are aggregate quantities, so we're allowed to share them. We share them on the central node, and they are added together. And then we simply divide the global sum and the global length to get the correct global average. Now, in order to arrive to a more general solution for the problem of implementing and building the federated algorithms, it will help a lot to have a visual understanding of what is going on with the previous examples. So we can visualize this computation using graphs where there is one operation per node, and we follow the computation from bottom to top. Here on the right is the graph representing the average computation if all the data were present on a single machine. So this is the non-federated computation for the average. So we start from some data, we compute the sum, we compute the length of this data, and then we divide the two results to get the correct average. Now, what happens when we don't have a single machine, but a federation? Then we choose some node. We can choose some node of the computation graph and replace it with this merge construct that I have on the right. So instead of having one operation and everything that precedes this operation, which is represented by the dashed lines below, we take this operation and we repeat it in multiple hospital nodes, and then the results of these operations are gathered and merged in the central node. This merge operation, which is the new box we have introduced here, the green box, is usually just a sum of the local results, but it can be other things also in a more general case. So this is the substitution we have to make on certain nodes in order to go from the non-federated to the federated case. Let's see what happens to the three solutions that I presented before for the average problem and how they translate to these particular graphs. So in the first case, we can place the merge operation here as shown on the left, where that means just that we take the data from the first hospital node, the data from the second hospital node, we merge them together in the central node, and then we proceed with the rest of the computation. As we said, this is a privacy violation, obviously, because we are exposing the individual data points to the central. In the second case, all the computation is performed locally. So it's the two diamond graphs left and right of this image. And then we wish that we were able to merge these results in the central node, but of course there is no correct way of doing that. Finally, in the correct case, the merging takes place somewhere in between. So it's a question of how far up we are going to push this merge operation. And this particular spot here is the sweet spot for the computation of the average for this particular algorithm. This leads us to the following general method. First, we express our computation as a graph. Then we mark all the nodes that are not privacy preserving. And by that I mean all the nodes that if we were to merge them, we would violate the privacy condition. Then we mark all the non-parallelizable nodes, that is, all the nodes that cannot be replaced by this merge construct because they would lead to wrong results. And then the remaining nodes are the candidates for being replaced by this merge construct that I showed earlier. Now, let's see how this would work in a realistic example, like linear regression. So in linear regression, one way to solve a linear regression problem is by the ordinary least square formula, which is shown here on the left. And we want to compute this quantity W, which are the coefficients of the linear regression model. And here, X and Y are the clinical data, and they are precisely the design matrices for the independent and dependent variables accordingly. On the right is the graph for this computation. So we start from the data below, on the bottom, and then proceed from bottom to top to compute this coefficient. So let's apply our method. First, we mark all the non-privacy preserving operations, which happen to be these three on the bottom, sorry. Then we mark all the operations that cannot be parallelized. And then we are left with the two nodes that are merge candidates. And indeed, this is able to lead to a correct solution that is both correct and privacy preserved, which is represented by this complicated graph, where green boxes represent the results that have to be shared to the central node in order to have a privacy-preserving and correct computation. So for completeness, I also present the pseudocode for this particular case. Basically, what it says is that for each hospital, for each local node, we compute this quantity x transpose x and then x transpose y. We share these quantities to the global node, to the central node, and then we perform with the rest of the computation. We sum together all these quantities, and then we take the inverse and the dot product, and we obtain the correct solution for the linear regression. Now, one interesting question is what happens if no solution can be found for some algorithm? That means, what if we mark all the non-privacy preserving nodes, all the non-parallelizable nodes, and there are no nodes left as merging candidates? Then obviously we cannot have privacy preserving and exact result at the same time, and something has to give. Of course, we consider the privacy rule to be sacred, so we have to relax the second condition, which is the exactness condition, let's say. And that means that we have to find an approximate solution. The graph construction that I presented is able to suggest possible approximations. Finally, once an algorithm is implemented, we go through a series of tests to ensure its validity. So let me say a few words about that. First and foremost, we test against some state-of-the-art implementation. This is the most important set of tests. We have hundreds of randomly generated tests where the state-of-the-art implementation runs on some data on a single machine. Then the data is split into multiple nodes, and our implementation is run on these multiple nodes on this data. In the end, we compare the results and we expect them to be identical to the state-of-the-art non-federated case. For the cases where no exact solution can be found, we have and where approximations have to be made, we have a non-inferiority testing framework. Basically, using some traditional hypothesis testing methods, we are able to test if our result is inferior or not inferior with respect to the state-of-the-art implementation. So in these cases, we cannot have an exact match between the results because we had to find an approximate solution, but we can still test the inferiority of our solution against the state-of-the-art. And finally, a third type of testing called property-based testing is used to verify some mathematical properties on particular operations. For example, in order to have correct merging and parallelizable nodes, some properties have to hold, like associativity and commutativity, etc., which can be verified using this property-based testing. So in conclusion, I presented a simple but well-defined way of decomposing an ordinary algorithm and recomposing it as a federated version of the same algorithm. During this process, some sound conditions were expected to hold. And here is a list of all the algorithms that we have so far in the MIP, where the above procedure has been used in order to construct these federated solutions. On the left, we have some standard machine learning algorithms, and on the right, we have some statistics algorithms. In most cases, we were able to find both exact and privacy-preserving formulations. On a few cases that was not possible, we were forced to come up with some approximations, which were then validated using the non-inferiority tests. Thank you very much for your time.